Alrighty, P. Chapter 12 is all about solids. It's a very short chapter since there are 4 solids that AP requires you to learn, and you are mostly going to go through the notes and annotate yourself. I'm going to point out a couple things. You can stop and pause as I go through, but first, these are the learning targets. Okay, so number 1, let's go through the targets. In a metallic solid, okay, so metallic solid is one of the 4. Valence electrons from the metal atoms are considered to be delocalized. Now, delocalized means that the electrons can move freely. They can move wherever they want, okay? And are not associated with any individual atoms, which means those electrons can go from one atom to a different atom, or they can go from one atom and stay in that atom, but maybe jump like energy levels kind of thing. So that's what they mean, they can move freely. So anytime you see that word delocalized, you definitely going to want to make sure that you understand what freely means, delocalized means. The cations and anions, so remember cations, those positive anions, those negative anions, and an ionic crystal. So ionic solid is another one. That is the next type of solid, are arranged in a systematic periodic 3D array that maximizes the attractive forces among cations and anions while minimizing repulsion. So very key right there. Oops, didn't mean to highlight that. Oops, go back. There you go. So maximizes attractive, minimizes repulsion. Metallic bonding is the next one, and it's going to go into more detail. Metallic bonding, metallic solids, can be represented as an array of positive metal ions surrounded by delocalized valence electrons. And we usually call these delocalized, aka electrons freely to move. We call them the sea of electron model. And you'll see tons of pictures in the notes that what the stuff looks like. Because you're like, what does this look like? What do you mean like 3D array, Rodriguez? What do you mean sea of electrons? Trust me, it's coming. It's coming. 3.2, many properties of liquids and solids can be determined by the strength and type of their intermolecular forces. Okay? Because intermolecular interactions are broken within substances that vaporize, and remember vaporize, we're talking about liquids going to gases. Sorry, did not want me to write in that box. The vapor pressure and boiling points are directly related to the strength of interactions. Okay, so remember the stronger the forces, the higher the pressure, the higher the boiling point. Melting points, I guess I can just write it right there. Melting points is when you're talking about the temperature in which to convert it from a solid to a liquid. Also tend to correlate with interaction strength. But because the interactions are only rearranged in melting, the relations can be more subtle. So not as noticeable as like a liquid to a gas. Particular level representations, as in particle level representation, which means drawings, showing multiple interactions, chemical species, are a useful means to communicate and understand how intermolecular interactions help to establish these macroscopic properties. So macroscopic, we're talking about big level properties on the big scale, okay? Due to strong interactions between ions, okay? Ionic solids. So right up here, where it's talking about ionic crystals is the same thing as ionic solids. And I want to put down some numbers where you're going to see this in the chapter 12 chapter. So ionic solids, you will see this in 12.5. Okay, so chapter 12.5. Tend to have very low vapor pressures and high melting points. Melting point, solids to liquids, that temperature, and very high boiling points. They tend to be brittle due to repulsions of like charges. Remember repulsion, like and like. And caused when one layer slides across another. And I promise you'll see some pictures. They conduct electricity. Okay, so that's what I said. You're just annotating some notes. And only when the ions are mobile, as in moving. And when the ionic solid is melted or dissolved in water or in another solvent. So they're definitely moving if they are melted or dissolved in water or another solvent. Network solid is another. Like I said, there are 4 solids, okay? And you will read about network solids in chapter 12.7, okay? The atoms are covalently bonded together in a 3-dimensional type of structure, aka diamond, this is what it looks like, or a 2-dimensional network, as in like graphite. And remember, graphite is pure carbon, okay? These are only formed from non-metals. Elemental, diamond, and graphite. Diamond and graphite, they're both pure carbon. So remember this thing called an allotrope, okay? It's pure elements in different forms. Most elements only have 1 or 2 different forms of it, but carbon actually has 3 different forms. So carbon could be diamond. That's pure, whoops, could not even spell diamond right now. Diamond. Carbon could also be graphite, like what you're writing with on your pencil. Ooh, bad spelling today. And you're probably like, Rodriguez, you always have bad spelling. I know. And also coal, as in like what we burn for energy. Okay, so diamond has 3. It's the only element that actually has 3 different versions of pure carbon. All right, so these are only formed from nonmetals, elemental, diamond, graphic, or binary. Remember, binary means 2. Okay, 2 compounds of nonmetals. Silicon dioxide, that's sand. Okay, and silicon carbide, that's obviously silicone and carbon. Okay, so Si and then C. Due to the strong covalent interactions, so very strong covalent interactions, they have very high melting points. 3-dimensional network solids are also very rigid and hard, okay, which means like rigid, they're not smooth, okay? So definitely has some type of I'm having a brain fart on the word I'm trying to look at. Think of like if you broke like a chunk of cheese, and if you looked at like the center of the cheese, it actually looks very rigid. There's no smooth edges to it, okay? Because the covalent angles are very fixed, okay? Graphite is very soft, and adjacent layers can slide past each other with very relative ease, okay? The next type of solid is what's called molecular solids. And you will see molecular solids in 12.6. And they are distinct individual units of covalent bonded molecules attracted to each other through relative weak intermolecular forces. Molecular solids have very low melting points because they're very, very weak, which means it does not take a lot of heat to make these guys melt, okay? So definitely low temperatures to melt them. They do not conduct electricity because their valence electrons are held very tightly. So these are what we call localized electrons, because localized means they're in a fixed position. Okay, delocalized means they can move more freely. Within covalent bonds and lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. Okay, and you'll learn in this very last one about polymers, which you probably remember a little bit from biology back in the day. And metallic solids. Metallic solid is the 4th one. So right here, if you look, you got ionic solids is number 1, network solids, molecular solids, metallic solids, okay? And I want to do a little mention on this one real quick. There are 3 types of bonding. You've been doing 2 of them forever, ionic and molecular. But we never, ever, ever get to give some love to this 3rd one. It's called metallic bonding, okay? So this is that 3rd one. So basically it's metals that have bonded with other metals. And I know that sounds a little freaky, positive and positive, but it does happen, okay? Now with this category, 2 very important things. You need to learn about what's called alloys. There are 2 types of alloys that you need to know, and you'll see their words popping up, okay? So metallic solids, you will see these guys in about 12.4, chapter 12.4. Metallic solids, very good conductors of heat and electricity due to free valence electrons, aka delocalized electrons. They're very bendable, malleable, and they like to be ductile, which means moved into wires, due to their ease at which the metal cores can rearrange their structures. You have one type of alloy called interstitial alloy, and I'm going to, let's do a different color. There's one of the alloys, and I know the other word is supposed to pop up somewhere. Interstitial atoms tend to make the lattice more rigid, decreasing mobility, which means not as bendable, and decreasing ductility, not able to draw on wires as much. Alloys typically retain a sea of electron, mobile electron type of structure, so they remain conducting. Okay, the other alloy, oh my lord, the name just, I know it starts with I want to say it's a S, substitual. Let me get the other name on here. Looking through my notes. Give me a second. Yeah, let me write that name down. Substitutional. Ooh, that's a bad word. Substitutional. And like I said, you'll see that word in 12.4. Those are the two alloys. In large biomolecules, about the one time you'll hear me say anything about biology or polymers, non-covalent will mean non-covalent as in non-metals bonding with non-metals. Okay, so non-covalent interactions may occur between different molecules in different regions. So different molecules, different regions of large biomolecules. The functionality and properties of these molecules depend strongly on the shape and largely dictated by their non-covalent interactions. So they probably have a little bit maybe of molecular type of properties or maybe ionic type of properties. So you're going to go through here, ladies and gentlemen, and you're going to read and you're going to annotate each one. You're first going to start with crystalline and amorphous solids. I know these two words, they sound familiar because we talked about them last year. And looking at the structure. As you're going through these notes, pay close attention to the structures of these type of patterns. These are the 4 type of bonds that you need to know: metallic, ionic, covalent, network, and molecular. And then, as I said, there are 2 alloys. Okay, so go through here and find the common traits and differences between them. Okay, and I'm letting you do this. So you're going to start with ionic solids and go through there. See, there's pictures that show you the difference of them. And this is what we call a 3-dimensional structure. Metallic solids, okay, metallic bonding. Okay, the sea of electron regions, as you see right here, the sea of electrons, positive and negative. The negative, obviously, the electrons. The positive is the nucleus. And I'm just going through this first, ladies and gentlemen, so you go through and read and see the difference. Here's the alloys, okay? Alloys can be divided into 2 type of categories. These are the 2 major that you need to know. And it has to do about the radius, okay? So right here, looking at the differences of the radius between the positive and positive. So you'll see, once you read it, you'll see the differences in the structures. So that way I can answer some questions to you. Heterogeneous versus intermolecular compounds. Okay, these are the number 3 and 4. But for the alloys, these are the 2 major ones. Okay. And then covalent network solids. This is when you would get like your diamond, your graphite, your sand, quartz, which is silicon dioxide. So just make little notes here. That's sand, silicon dioxide. And that's what their structure would look like. And then semiconductors basically means they conduct electricity, just not fully. And then molecular solids, those are what molecular solids look like. Looks like a bunch of water molecules in a solid type of structure. And some practice AP questions. Now, ladies and gentlemen, there's not many questions I can give you because AP hasn't done too much with solids in the past. This is a new thing. So right here in College Board video, right here in 2.1, 2.4, these are the only two free response questions they have done in the past 10 years. So it's a very rare topic, but we still need to see it before that test. So about 36 minutes, you'll answer this question. And then I believe right after that question, around 39 minutes, this is the next one. Okay? And that is it, ladies and gentlemen. Have fun.